Okay, hi, Chem 30, new lecture here. I'm going to review on your nomenclature assignment some halogenated hydrocarbons on your sheet. I'm not going to do all of them, but you'll get the general idea. And then I'm going to talk about alcohols and carboxylic acids in this lecture, and then those are all, other than esters and polymers, those are all the hydrocarbon derivatives that you guys need to know about. So let me do some examples of halogenated hydrocarbons that you have on your nomenclature sheet. I'm going to look at 4E. Actually, sorry, I'm not going to look at 4E. I'm going to look at C. 4C. So this is 4... Oh, my pen's running out of ink here. Fluoropentuene. Okay, so to draw this, 1, 2, 3, 4, 5. I'm going to have a double bond on carbon 2, so that's pentuene. Now, so remember that these halogenated hydrocarbons can be attached to alkenes and alkynes. The naming rules are the same. You just need to consider them in the actual reactions. They could also be on benzene molecules or on cycloalkanes as well, right? I showed you some benzene molecules with halogens on them. And in fact, a lot of benzene molecules will have halogens because they make really useful molecules for us, different types of pesticides and herbicides, for example. But let's go back to this 4C, 4-fluoropentuene. So here's 1, 2, 3, 4. I'm going to have a fluoro molecule on carbon number 4, right? So it's the same rules. The double bond takes precedence over the side branch when naming. So this is closer to that terminal carbon. So that's why this is carbon number 1. Okay. Let's look at B. B's a bit more tricky. So this guy, this has a side branch and it also has halogens on it. So this is 2,2-dichloro 4-propyl heptane. All right, so here's the molecule. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. So heptane. I'm going to have chlorine, 2 chlorine molecules on carbon 2. 1, 2, 3, 4. And then I have a propyl molecule here. And that's what that would look like. Okay. So 2,2-dichloro 4-propyl heptane. That's an alkane, right? It doesn't have a double or a triple bond. Let's look at some of your examples on here. So you have some bigger molecules. Right, this is, let's look at this one. Now this is a single bond. There's a A here, 5A, bromine and methyl group. So you should be able to name that yourself. This is an alkyne, right, with bromine on the end. This is an alkyne with bromine on the end. This is a cyclomolecule of fluorine and bromine. So let me look at C. Okay, so this is okay, so that's what this molecule is. So my longest branch, I'm going to number here because my triple bond is on this carbon. This bromine's on this one of these N carbons here, but again, the triple and double bonds take precedence. So this is 1, 2, 3, 4, 5, 6, 7, 8. All right, so this is actually oct 1 ine, and that's on carbon 7. So that's 7 bromo. Oct 1 ine, and that's how I would name that. Okay, this is dodecane. So this is 12 carbons as your parent chain. I'm going to leave that for you to name, though. You have some chloro molecules, propyl, ethyl, and methyl groups on that. And I'm going to do this one. So this shows cyclopentane. And that would obviously be my carbon 1. So this would be 1 bromo and then 1 fluoro cyclopentane. Okay, and I just number carbon 1 because that's where my side branches are. All right, and you name it in alphabetical order based on the element itself. Okay. Let's look at some of these molecules. Now this one, so D, this one's a weird one. Okay, so this has chlorine. Now remember, chlorine has 7 electrons. So there's only 1 bonding spot, but there's 1, 2, 3 bonds attached to it. So this molecule is not actually possible. So you should cross that one out. All right, so that's kind of a trick. This one is a halogenated hydrocarbon that I talked about already. And then this one I'll do as an example. So H. Okay, so again, I'm going to name my carbon from this carbon 1 because the triple bond's here. So this is 1, 2, 3, 4, 5, 6 carbons. That's my parent chain. So this is going to be hex with a triple bond, 1 ine, hex 1 ine. And then I have a bromine group, and that's on carbon 5. And then I have a chloro group on carbon 3. So this is going to be 5 bromo, 3 chloro, hex 1 ine. Okay? So that's a little bit of review from the last lesson on halogenated hydrocarbons. I want to move on from that, and we're going to talk about alcohols. Okay, so just give me a sec here. Okay, so here's your functional group for alcohols. Is at the end of a carbon chain, you have a hydroxide group. Okay, so it's always going to, for the most part, be at the end of a carbon chain. This is what a typical alcohol looks like. And again, this is 1 carbon, so this is meth. Now, alcohols, the hydroxide, what you should understand is it's not a base. It does not act the same way as the anion hydroxide. It's bonded to a hydrocarbon. The OH group is known as a hydroxyl group, not as hydroxide. So when it's in combination with hydrocarbons, the OH acts different than hydroxide. So you should take notes, read page 425, 426 in your text on alcohols. I kind of summarized them here though. So hydroxide gives them polarity, so they're very strong solvents. What do we use them for? Disinfectants, fuels, right? Ethanol, you add ethanol to petroleum, right, in order to increase the amount of oxygens present. We talked about incomplete and complete combustion yesterday. So if the fuel burns cleaner as a result. We use alcohols in pharmaceuticals. And obviously, ethanol is the main type of alcoholic beverage that we consume, right? It is, socially acceptable drug. So methanol and ethanol are the 2 most common alcohols. Methanol is a disinfectant in mouthwash, and we use it in antifreeze as well. We also use ethylene glycol. Ethanol is added to gasoline to increase octane, reduce emissions. It's used as a gas line antifreeze because of its low melting point. And this is ethanol itself as well as also, our main social drug of choice. All right, so how do we name alcohols? You find the hydroxyl functional group and circle it. Determine the parent chain of carbon atoms, starting at the nearest end closest to the hydroxyl group. Use the method of naming hydrocarbons as we've already done to determine the initial part of the name. Now we name alcohols like this. So the location of the hydroxyl group on the parent chain. So you name the location of the hydroxyl group. Add the suffix that represents the presence of a hydroxyl group. So you drop the alkane or the ANE or ENE or YNE, drop that and add OL. So rather than something being ethane, it's now ethanol. Okay, or methane is methanol. Okay, so you drop the ANE or ENE or YNE, drop that and add OL. Okay, so alcohols as well containing 2, 3, or 4 hydroxyls are called polyalcohols. All right, so if there's more than one hydroxyl group, if there's 2 hydroxyl groups, we call the alcohol a diol. You could have triols and tetraols. All right, so and I'll give you a bunch of examples that look like that. You could also have different degrees of alcohol. So if I have an alcohol that's right, if I have the carbon on a primary alcohol is only bonded to one, right? It's not bonded to any other carbons. Okay, so primary alcohols have an OH on a terminal carbon, so since there's only one other carbon bonded to it. Secondary alcohols they sit in the middle of a hydrocarbon chain, so they have 2 carbons attached to them. So this would be a secondary alcohol. Tertiary alcohols, right, the carbon has a hydroxide attached to it, obviously, or hydroxyl, but then there's 3 other carbons attached to it. Okay? So primary alcohol, the terminal carbon only has 1 other carbon bonded to it. Secondary alcohol, there's 2 carbons bonded to it and it's in the middle of a chain. Tertiary alcohols have side branches and a main chain attached to them, plus the hydroxide group. Okay? Page 428 and 429 have samples of what these primary, secondary, and tertiary alcohols look like. Okay? So let's do some examples. All right, so let's start simple here. This is butanol. So butanol. All right, if I were to draw a line structural diagram, 1, 2, 3, 4, there would be a hydroxide attached to that. Okay, that would be butanol. All right, this would also be butanol. So 1, 2, 3, 4. So this would be butan. This would be on carbon 1. So that would be butan-1-ol. I could have a hydroxide attached here, and this would be butan-2-ol. Right, and this would be, that's a primary alcohol, and this would be a secondary alcohol. Now I could also have this, let's say, I have that, right? So now this is butan-2-ol, but this is 2-methyl butan-2-ol, and this would be a tertiary alcohol, right? Because the carbon group is attached to 3 other carbons plus the hydroxide. Okay? If I were to represent this as let's say I take this guy and represent it as a condensed structural diagram, it would look like this. Okay? Or if I wanted to, I could represent the C like this. Right? And make that complete structural diagram and show all the hydrogens. All right? But this is how I would represent that. Okay? So let's say we have this. So as I said, you could have diols or triols. Again, this is 4 carbons, so this is butanol. So this would be butan. This is carbon 2, so butan 2, 2. And this is on carbon 3. And this would be a triol because there's 3 hydroxyl groups attached to that. All right, so pretty simple. And I don't have to, I won't just use butanol, but let's say we have this guy, 1, 2, 3, 4, 5. This would be pentan 2-ol, right? Pentanol. Okay. Let's look at a couple more. Three carbons, right? So propan. So rather than propane, I drop the A and E and add propan-ol. So propan 2-ol, because that's where it is. It's on carbon number 2. Let's look at this guy. Okay, so I have 1, 2, 3 as a parent chain. This hydroxide's on carbon number 1. This would be my carbon number 1 because it's closest to the functional group. So this is propan 1-ol, and there's a methyl group on carbon 2. So 2-methyl propan 1-ol for this molecule. Okay, condensed structural diagram again. That's on carbon 2, 4 carbons, butan 2-ol. Right, so this would work for any of the top 10 prefixes, right? Octanol, nonanol, hexanol, heptanol, right? The rules are still the same. Let's look at this guy. Let's say I give you this as a line structural diagram. Okay, so I have 1, 2, 3, 1, 2, 3 carbons as my parent chain, and a hydroxide on carbon 2. So this is propan 2-ol, and I have a methyl group on carbon 2. So 2-methyl propan 2-ol. Let's say we have this. So rather than a methyl group, I have another hydroxide or hydroxyl group. Okay? So this would now be propan 2,2-diol. Okay? Now let's say I give you this one. There's a carbon number 1 here and a carbon number 2 here. So that kind of looks weird, but where the break is where the extra groups are. So this is going to be 3 hydroxides, so that's triol, and there's 1, 2 carbons, so it's F-an 1, 1, 1 triol. Okay? And last one. Okay, so 1, 2, 3, 4. This is a diol. There's 2 alcohols or hydroxyl groups. Carbon 2, carbon 3. So 2, 3. Butan 2,3-diol is how we would name that. So those are general naming rules for alcohols. Okay? So, problems to deal with alcohols. Page 430, numbers 5 through 11, and then numbers 13 and 14. Okay? All right, so let's look at this. So let's say draw the structural formula of the following alcohols and indicate if the alcohol is primary, secondary, or tertiary. Okay? Pentan 1-all. Alright, so let's draw this. It's going to be on carbon number 1, so there's my hydroxide. The carbon is only attached to one other carbon, so that's a primary alcohol. What about this one? 4-methyl cyclohexanol. So it would be hexan 1-all. So let's say I put my hydroxide here. So I go 1, 2, 3, 4 carbons over, and there's my methyl group. Okay, so that's what that would look like. Here's the carbon that's attached to the hydroxide, and it's attached to 2 other carbons. So that's a secondary alcohol. Okay. Now I can have alcohols in combinations with halogenated hydrocarbons as well. So let's say this is 5-chlorohexan 1-all. Or sorry, hexan 3-all. Okay, so a hydroxide here. What this means is the chlorine will be 2 carbons away from the OH group. All right? So this is the structural formula for that. This is not actually how I would name this, so I would rename it properly. So this is actually carbon 1. Okay? So the proper name for this is hexan all, but it's actually 3-chlorohexanol. So again, you have to have this skill. Right? If it's named improperly, you need to be able to name it properly. Okay? And again, this is a cycloalkane, so here's your carbon attached to 1, 2 other carbons. That is a secondary alcohol. And then let's say we have this. So this is 1, 2 alcohols, that's a diol, and this is on carbon 1 and 2. And so this is propan 1, 2 diol. And again, this would be, so this is actually a primary and a secondary alcohol at the same time. Okay? All right, cyclic and aromatic alcohols. You can see this, right? C6H11OH. But remember, benzene is C6H6. So if we have a hydroxide attached to benzene, what that means is a hydrogen is swapped out for a hydroxide. So C6H11OH is cyclohexanol. But this shows the C6H6 plus an additional molecule. So this would indicate a phenyl group or a benzene alcohol. Okay, so phenol, Phenol, not YL. So a phenol are aromatic compounds, so benzene alcohols, in which the hydroxyl group is attached directly to the benzene ring. Phenol is the parent compound with this, okay? So aromatic alcohols are named cycloalcohols as well, and I gave you a bunch. But if I have a benzene ring, that looks like this, okay? With a hydroxide group, that's no longer called benzene, that's called phenol. So don't confuse that with this as a side branch. This is phenyl. Phenol means aromatic alcohol. Phenyl means aromatic side branch. Okay? So this would be phenylbutane, right? And this is its own molecule unto itself. All right? So where am I going to see this? So these, you should take a look at this in the textbook. Polyphenols are very prominent in your diet. So polyphenols are multiple ringed aromatic alcohols, and they give us lots of different types of flavors. They're also the basis of antioxidants in a lot of our foods. Okay? So it's said to have antioxidant capabilities because of the hydroxide group. So what antioxidants do, I talked about this with the halogenated hydrocarbons. Antioxidants remove free radicals from our bloodstream. They remove charged particles, right? So the breakup of the ozone layer was because of CFCs, or chlorofluorocarbons. What happened was Cl negative and F negative ions ended up in the stratosphere, and those were freely moving charged ions, which collided with oxygen, the O3 molecules, and broke that up. So we reduced the ozone layer because of that free radical damage with the free floating charged ions at the top of the stratosphere. Now, you also have free radicals that move through your bloodstream. Okay? So anytime you take in aromatic hydrocarbons that have halogens, those will break up into your bloodstream and diffuse in there. Through oxidative damage, just through breathing, you create free radicals. Your DNA is negatively charged, so it will interact with free radicals. So if we have antioxidants in our diet, the antioxidants, what they do is they bond with free radicals that float naturally in your body and remove them so they don't cause DNA damage or mutation. So as a result, these polyphenols, which tend to be free radicals, are very healthy in our diet. And they have anti-aging effects and anti-cancer effects and lots of different types of indirect health effects. So grapes are full of these polyphenols. And the types of polyphenols they have are flavonoids and resveratrol. Right? So that's why a lot of people say things like wine is like a healthy alcoholic beverage for us. Now there is no healthy intake of alcohol daily, right? So eating grapes is a lot healthier than drinking wine, for example, right? But the flavonoids and the resveratrol in the wine that comes from the grape actually has lots of antioxidant properties. So this is a whole list of aromatic alcohols that exist in our diet. So you can see flavonoids. There are, what else do I have? I have tannins, which I get from tea. Different types of monomers and organomers, flavonones, isoflavones. There's lignins. So there's all sorts of different types of these free radicals. Okay. Again, tannins we get from lots of different types of tea. But here's a good way for you to figure out if you're getting enough antioxidants in your diet. Now, the more colorful your diet, right? So plant pigments are created from polyphenols. Okay? So the coloration of plants come from polyphenols. because polyphenols are in photosynthetic pigment. All right? So if you have a more colorful diet with different types of fruits and vegetables, you're getting all sorts of different types of antioxidants. Okay? And this, right, so this shows a whole bunch of different types of antioxidants. And typically the darker or more colorful the vegetable or fruit, like blueberries for example, the more full of antioxidants they are. So they can remove free radicals from your diet. Now if you eat a lot of Skittles, that doesn't count. Right? So that's just food coloring, right? So, but if you have a very balanced diet with lots of different types of colorful vegetables and fruits, then you're taking in the plant pigments that create all the different plant colors, which helps with photosynthesis at different ranges of the electromagnetic spectrum. And the polyphenols are the basis of these molecules. Okay? So this information is important for diet. How much time do we have?
3 minutes.
Okay. I'm going to end this part of the lecture here, and we'll talk about preparation of alcohols and carboxylic acids in another lecture.